Hi, all, and welcome back to this paging series of videos on memory management in OS. So, we were discussing about paging and we discussed certain questions based on paging. Lastly, before starting performance of paging, I would like to conclude this entire series with last thing that I mean to say about page table entry and what is the optimal value of a page size that will be required in the memory for storing the entire page table. So let me illustrate. Let's say we have a system with an LAS equal to S bytes. Okay. So this is the our LAS and we have a PAS equal to S bytes. So both are equal basically. And we have the page size, or you can say the frame size, equal to p bytes. Okay, so here we can calculate the number of pages equal to s upon p, and here we can calculate the number of frames equal to s upon p. So s upon p will be the number of pages and the number of frames. Okay, now PTE, that is the page table entry, which contains the frame bits or the translation bits, we already have discussed. Okay, so the PTE size is e bytes. Okay, so this is e bytes. Now if we ask that what is the value of optimal value of page size page size by minimizing memory overhead, memory overhead of creating and maintaining page table, of creating and maintaining page table size, page table size, and internal fragmentation in the paging. We already have discussed that internal fragmentation, maximum internal fragmentation can happen in the last page, and that could be p by 2. That maximum could be p by 2. Okay, so maximum internal fragmentation can only occur in the last page, that is when we divide the pages. So in the very last page, the maximum fragment in maximum internal fragmentation could be there, and it could be considered as p by 2. So what is the value of the page size? Page size already given p, so we are asked about the optimal value of p by minimizing memory overhead of creating and maintaining page table size and internal fragmentation. Okay, so we already know number of pages. So number of pages equal to s by p, number of frames equal to s by p, and entry size is e. Entry size is e. So if we say that what is the page table size, so we can write the page table size equal to number of pages into entry size, that is s by p into e, that is se upon p. So this is the maximum page table size we can assume. Now comes the internal fragmentation part. So the internal fragmentation could be p by 2. So we have to minimize the page table size, that is pe by 2 and p by 2. Now to minimize this, we will do what? We will differentiate this. So d upon this much upon dp, and we have to make it equal to 0 because we need to minimize this part. So we will go for differentiation. So what it will be, e by 2 will come out of this. So e by 2, okay, sorry, it is sp by 2. It's not p by 2, it's p by s by p, sorry, it is s by p. Okay, so upon p. So this is we can write sep upon minus 1. So it will be minus Se upon P square plus 1 upon 2 equal to 0. Then it will come as Se upon P square equal to 1 upon 2. So P square is equal to 2Se. So P equal to under root 2Se. So this is the optimal page size to minimize the page table size PTS plus the internal fragmentation, that is considered as P by 2, right? So this will be the answer. So this is just a discussion about the page table size and page table entry. And before that also we have discussed a lot of small questions onto this. So now it's time that we will go up ahead into another topic called performance of paging. So let me start another page for performance of paging. Performance of paging. Right now, what is this performance of paging? So obviously we have used this page table to convert this logical address being generated by the cpu into physical address. But why are we using this conversion? Why are we not directly accessing the logical memory to access our pages and get that from there, so as to minimize, so as to improve the performance, right? For example, we use cache memory so as we can improve the performance time. We have some usually most referred pages present in the cache memory, so that the processor time, that access time that the processor takes for accessing those things, it is lesser, right? In the similar way, here also when we introduce this paging part, then how what is the total access time when we introduce paging into the picture, right? So let's see for that. So let's say the main memory access time is m. Okay, now page table are also stored in the main memory. Is it correct? So for every process, we are storing the page table, and we are creating the page table, and the page table for every process are stored in the main memory. Okay, so for accessing the page table also, it requires m time. So we can write that effective memory access time is 2m, because first we will access the page table, we will find in which frame our page is present, and then we will access the frame, that particular frame number in which our page is kept, and this is placed also in main memory. So the effective access memory time is 2m. Okay, now the translation look aside buffer is added to improve the performance of paging. You can assume that the translation look aside buffer is just like a cache. So we can write the translation look aside buffer, that is also known as TLB, translation look aside buffer, is added to improve the performance of paging. Is added to improve the performance of paging. Okay, so it is similar to cache memory. So what does this TLB consist of? Okay, so this TLB consists of frequently accessed pages. Okay, so TLB contains frequently referred or frequently asked for pages by this processor, frequently referred pages, and their corresponding page number, sorry, corresponding frame number, and their corresponding frame number. Okay, so TLB is just introduced to improve the performance of paging. So TLB is basically a hardware device. hardware device which is implemented by with the help of some associative registers, okay, which is implemented with the help of some associative registers. It is a hardware device implemented with the help of some associative registers, and TLB access time is very less. TLB access time is very less compared to memory access time. Okay. So this is thing for that TLB is used. So you can assume TLB just like a cache memory. Cache is also hardware being introduced with the help of associative register. So it contains the frequently referred pages and their corresponding frame number, and it is being introduced to reduce the memory access time, which is from 2M to something else, right? So we will see how does this addition of TLB helps in reducing the overall access time. So let's say the CPU P has processor P has generated something called logical address that contains P and D. So 13-bit logical address it has generated. Now, uh, so what happens first? This address goes into the TLB. Okay, now TLB will contain some of the pages, some of the frequently referred pages, and the corresponding frame number. Okay, so in the TLB, if it is like it will contain the page number and their corresponding frame number in which this page is present. Okay, so if this TLB is a hit, if page number is found in the TLB, then definitely it will go to where? It will go back to the PA. Okay, this diagram is getting very curvy. Let me redraw it. Okay, so if it is a hit means that if the page number is being found in the TLB, then what will happen? Corresponding frame number is generated, and now for corresponding frame number, now if we have got the corresponding frame number, then we will go back to the physical address of this, and from here we will find that for this frame, this offset is there. So this will refer to this frame number, and from here we will go back to the main memory to access the particular page. So this is the main memory, and from here we will access the particular page. Now let's say if it is a miss, so the corresponding page is not found, then we will go to this page table. Okay, and from here we have for every pages present in the main memory, we have their corresponding frame number. So if there are altogether 8 pages, so for all 8 pages we have why I'm spelling 7 8. Okay, so for all this 8 pages, we have the corresponding frame number, right? So from this frame number we will be going to this, and from here we will be going again to the memory. So actually, if the page number is present in the TLB, no need to go there, we can just skip this step, and we can directly go to the main memory to access that page. But if there is a miss here, then we have to go via this page table, and then the corresponding action would be taken to fetch this page from the main memory. Okay, so basic procedure is like if the TLB access time is C, okay, and the main memory access time is M, right? So what happens that here this all is this is also accessing time as M because it is also placed in main memory. So if TLB is a TLB is a hit, so we will take C plus M time, because C is the time for accessing the TLB and M is one time we are accessing the memory to get the particular page number. But if it is a miss, then First we are accessing the TLB, it is a miss. Then we are accessing the memory. Again we are accessing the same memory for the corresponding fetching the page number. So it is C plus 2m. So let's say if x is the probability that the page resides in TLB, then the corresponding access time will be C plus m. If there is a miss, that is the page doesn't resides in TLB, then it takes C plus 2m time, right? So this now becomes, okay, okay. So this now becomes the entire total time to access the TLB. I'll just redraw this diagram further because this is very much confusing. So right now we have calculated the memory access time, effective memory access time is equal to x into C plus m plus 1 minus x into C plus 2m. Okay, where x is the hit ratio, that is the page probability of the page being found in the TLB, and 1 minus x is the miss ratio, that is the page not found in the main memory. So if the page not found in the main memory, then this accessing will include, but two times we have to access the main memory. But if it is found, then only one time we have to access. Now let me redraw it again and will illustrate it further. Okay, so this is our CPU processor. Processor generates LA, that is the logical address, 13 bits. This is the page number and this is the page offset. Okay, now first this request will go into the TLB. Now TLB is nothing but something like an associative cache that contains frequently visited pages or frequently referred pages. So it contains the page number. Let's say it contains one or two page. So this 012, this is the page number it contains, and corresponding frame number it contains. So where this page is present, let's say in this is present in second, this is present in third, you can write it as like this, 000110, like this. Okay, and corresponding page number is 00100110. Okay, so from this 3 bit it will go here, it will find that whether this page is present here, and if it is present here, then in which frame we can find out this page. So this frame bits is there, frame number. Okay, so this is TLB, and TLB accessing time is C. So if it is a hit, like if it is 010, the page number access that is being required by CPU is 010, and it is present in second frame, we can find it here in the TLB. So if it is a hit, let's say it is a hit, so we will go back to the to generate the physical address here, and from here we will generate the physical address that will contain the frame number and the page offset or the frame offset. So this becomes let's say 2 bit, that is 10, and corresponding the this will be equal to this, right? So this is F, and this is D, and this is the known as PA, physical address. Now we have got the physical address. Now what will be the last step? To just access this into the main memory. So we have this main memory, and for this main memory we have all these pages being present. So for every like this is a 4 kilo word main memory. Okay, so 00, 01, 10 and 11. So from here we get that, okay, in second frame our second page is present, so we will be accessing from here, right? So let's say it is P7, P5, P3, and P1. Okay, so if it is present it will access it from here. So let's just erase it for now. Let's say now it is present, so we have found it, and it will take C plus m time. So C time for accessing this TLB and M time for accessing this main memory. If it is a hit, like X into C plus M. But if it is a miss, let's say it is a miss, so nothing is there in this. So we have deleted every entry. Now it is not there anywhere in this. Okay, no frame number for any page is this. So it is a miss. So in this case, we will be accessing the page table, which is again in the main memory, whose accessing time is M. And for every page here, we will find the corresponding frame number. So if there are altogether 8 pages, for every 8 pages, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 100, 101, 110, and 111. For every page number, we have the corresponding frame number. So from here we will get this frame number, and then we will be again accessing the main memory for getting the page. So it will be C plus 2M, one time accessing this and then another time accessing this. So it will be 1 minus X into C plus 2M. So this way our total access time becomes this, right? So in this way we can calculate the effective memory accessing time in case of TLB. We'll see some questions related to that, and further we will discuss about the second type of paging called inverted paging or multi-level paging. Okay, till that keep watching the video, and if you have any question in understanding this concept, then please do share your comment, and thanks for watching.